Thank you, thank you. Well, well, well. Here we go again. Great ending question. Yes, I'm on the faculty at both the Juilliard School and the Manhattan School of Music. So when it comes to classical music, we're probably not going to get along. No, that's not true. Actually, a lot of my music and work is not so classical. But I was indeed here as the artist in residence for the Center for Genomics and Systems Biology last year. And of course, the first thing you want to know is who's better, Henry or Sam? The answer is, of course, Henry. But also, the other things you're going to figure out is that we do have differences. One of them is Henry mentioned that his goal is to learn as much as possible. And when I came, that was not my goal at all. My goal was more to force my ideas on the sciences here. And so we're going to talk about that now. Usually, at the beginning, I am indeed a musician. I'm a trumpet player, a composer, and sound artist. Usually, at this point, we sit and watch a video. We don't have time to hear that. You can just imagine that I'm playing well here. Here are some of the people that I perform with and work with. Velvet, John Cale, he's not classical. Nor is Laurie Anderson, nor is John Zorn. So, okay, safe for now. But as a performer, I am a trumpet player and a composer and sound artist. And here I'm playing in this water reservoir, this decommissioned water reservoir outside of working with scientists and performing with others. A lot of my interest looks at unique acoustic spaces and places that were designed not for music, but the way they affect musical composition and the way we think about both composing and performing. It's interesting, I've become the water reservoir guy. From here, I go back to the United States, and in a couple of weeks, I have a commission inside a 15 million gallon water reservoir, a cistern in the city of Houston, Texas, that lives beneath the city. And I'm there to, this piece that I was commissioned to write using water data, environmental water data, that's going to be transformed into both sound and light. Which brings me to the stuff that also brought me here, and the thing that we talked about, which the thing that says right on the very first slide, this idea of policy. I'm going to make a comment about that, the idea of art, science, and policy. But as a composer and a sound artist, a lot of my work looks at the relationship between humans and the natural world, thinking about it and ways of sharing ideas and connecting to both data and also just our particular relationship, looking at our nature and looking at how we have forgotten our connection to it. And so how I've been working on that and working in this field is looking at projects that center natural processes at the core of the design. And some of those things include sonification. So if we think in science, visualization, take your fabulous data and turn it into visuals. There's another way of taking data and turning it into sound. And perhaps that's part of what you were thinking about and talking about when it comes to science. Not only is it also connected, we can turn things into sound that connect to other genres of music, but we can also turn them just into sound, like the idea of many of the ideas of frequency and amplitude being the principles of which we then assign information. And we can also then stretch it further, which you'll hear a little bit today, the idea of then taking it and then going further beyond just the data and musifying those sounds. So some of the projects that I've worked on that relate to this field and these ideas are designing sound installations and light installations that use biological processes that are being recorded in plants and then translated into sound and light. You can see in these little videos looping behind me of me noodling around in a forest on an island off the southern coast of Tasmania, making a public installation based in reading information from the plants, and then something down here that was designed for Colby College for the opening of a new art and innovation space, which took data from plants that were on the forests, on the campus's forest. Other things are using earthquake data, working with the US Geological Survey and the national parks in Hawaii as the artist in residence for the national parks in Hawaii, turning the earthquake data into sound and for the creation of new musical scores, which show us the variation, the frequency, and the difference in what's happening underneath Hawaii and how it's changing the shape of the island and indeed the very face of the earth. Using soundscape recording, live soundscape recording, particularly in forest with special technology called ambisonic recording. We can record the three-dimensional soundscape of forest, which then being imported and placed in other spaces. This is to do with also a project that I've been working on with the European Commission, both the Directorate General for Environment and also the Joint Research Centre, that looks at the relationship between humans, nature, and of all things artificial intelligence, but I'll show you. Sadly, we're going to skip that project today for a limited time. Other silly things I've done are scored rhythms for historic thunderstorms, like the Hector thunderstorm that appears every afternoon between September and March above the Tiwi Islands in the Northern Territory and shapes, between September and March, that shape life on the island for the indigenous population there. And then the things we're going to look at, updates of what I was doing here, is turning genomes into sound, and we have a little update on that project, and also working with John Burt to start a project that looks at a brand new soundscape study of the coral reefs here in the Arabian Gulf, both for scientific and artistic outcomes. So, before we get to our fabulous CGSB stuff, I want to make a comment that's, I guess, the underlying part of this. You know, Henry is talking about his work and how it relates, and he's also, of course, talking about kind of the nexus of art and science. So I'm also here. I was here at the CGSB. Henry's also in other institutions that don't typically have artists as part of it. And I want to make the comment that this is happening more and more, and it's happening in many places. I think that the disciplinary silos that we have been forced into in both academia and also in government organizations and even in private enterprise are starting to break down. And as Professor Boisineau mentioned, the idea of interdisciplinary work or transdisciplinary work being important for NYU, which is really fabulous, it's becoming more and more important for many places. And the Joint Research Centre, part of the European Commission, essentially the government of the European Union, started to look at ways in which we need to break these things down. The idea of combining artists and scientists and policy officers as a way of looking at how we make changes in society. And so in 2022, I was very fortunate to be among 20 international artists who were invited to the Joint Research Centre to learn really first about what work scientists were doing and policy officers were doing regarding the European Green Deal, the idea of the very lofty goal that the European Commission is trying to make the European Union carbon neutral and do it really kind of quickly. And so we were learning about all of the research that's happened both on the scientific side and the potential policy that was trying to be implemented for this very big goal. And then those 20 artists, we were invited to work with scientists and policy officers to pitch projects that could be either new interdisciplinary, transdisciplinary research, or projects that looked at things like policy that are implemented to create public artworks that could then connect to the public, considering these things are going to drastically affect life in the Union. So it really is this transdisciplinary idea, the idea to connect science and art for society. And when I first arrived there, it was interesting. The very first opening talk with us opened with the idea from a director who said, "It has gotten so bad, we've called in the artists," which I find fabulous and interesting, and also very sad. The underlying for that is the concept that the concerns are that science, if we want to make real big societal change, if we want to make significant policy change, that science may no longer be enough. And so it's the idea that also incorporating broad minds or different thinkers from various disciplines to come together has the potential for solving the complex problems that we face in society now, and also just the idea that we must look beyond just science to be able to implement it in a real actionable way. So one of the projects I will show you here that I did work on, and it was open in Brussels for 6 months last year and has just gone to Bogota, is a project called Anthos. And it was designed with myself along with 2 other artists, a Greek data and visual artist and a Colombian visual artist, and 3 scientists. One focuses on, is a wild bee expert. Another is focusing on food security, and the other is a complex systems modeling scientist. And Anthos looks at the relationship between plants and pollinators. And at the time, the backdrop of this was the idea that in the commission, there was a push to change policy on pollinators. And what we were doing is together we came up with this idea to look at those plant pollinator networks and connect with the public more, to show kind of the fragility, the strength and fragility of the network between plants, pollinators, and their co-evolutionary processes, and what happens when the climate crisis starts to affect those things. Things like drastic changes in CO2, heat, and humidity, and how we can demonstrate that in a way where audience members or the public can connect more deeply and understand both the research and also this idea of why we need to consider these things and change policy. So working together, it was to both understand how these things are being affected, and of course the wild bee expert has a lot of data over years that look at the way these changes affect certain categories of plants and certain categories of pollinators. So when I say the plant pollinator networks, it is plants and it's pollinators and how they interact, and it's different kinds of plants and pollinators. Of course, certain pollinators can only pollinate certain plants, et cetera, et cetera. You all know these things. And so the goal was to also recognize ways in which we are reliant on these networks, and also look at it further to do with not just kind of an anthropocentric focus, but also on biodiversity in general. And then together, we worked on building a model that represents all of these things, and to create an interactive installation. I'm going to show you a small sample of that now, a 1-minute sample. Actually, I think I'm speaking in it, so you don't get a reprieve from me, my talking. It'll just be recorded talking, not live talking. But the idea here is that you'll see in the space, you'll see nodes and lines, a classic network, and there's various nodes representing various, let's call them categories of plants, and you'll see all the little pollinators flying around. And this is being live projected. If you know Conway's Game of Life, for example, it's a version of a network of life that's sped up based on European biodiversity models in the knowledge of how plants and pollinators are working. And then you'll see all the data is on a ticker along the bottom of the space. And you yourself, you enter this space. You and your best friends go to this museum and you see this sound and light installation, and you walk in it, and by being in the space, we also have live environmental live environmental sensors, and they're recording changes, ambient changes in the room of CO2 and heat and humidity that you yourself project in that room. So it's a model of what's happening on a much larger space. And then you can see how you, inside that, are then affecting how the network grows, operates, whether it's going to proliferate, whether it changes, and where the equilibrium part of that breaks, and then the network breaks down. And so that was the idea of it, and it was the idea of connecting these things. Hopefully it looks fun and exciting, but of course there's a really terrifying potential underlying research underneath. So here is a small sample of Anthos and what's been happening in Brussels with the Commission. And interactive installation that highlights the importance of pollinators and demonstrates our anthropogenic effect on them. Audiences enter a space where they can experience the simulation of a plant pollinator network based on European. Sensors inside the installation register changes in live environmental data affected by the audience, from rising and falling of CO2 emissions to variations in temperature and humidity. These audience-induced changes are then projected visually and heard sonically through the spatial sound design, affecting the rules of the complex system that underpins these plant-pollinator relationships. The greater the number of people inside the space, the greater the effect on the network. The system's ability to maintain an decline or ultimately fail is a product of human intervention. Calculating and generating visuals and audio in real time, Anthos demonstrates how the climate crisis is putting a strain on these natural pollinator relationships. The cutting out of the audio is not in the design. That's not part of it. I don't know what's happening there. So that was one of the projects within the Commission, and that's the idea of connecting artists and scientists and policy officers. Not that I need to prove to you why artists are important. I feel that. I am that. You have to prove to me why science is important. No, that's not true. You've already done that. But here, that's what's happening in the commission. And then here, I see so many familiar faces. So many of you are going to know some things already about this project. And you can just switch off now because there are still some fresh faces. And we can't skip over this stuff for the people who are new in the room. I was here last year with the CGSB and started two collaborative projects that we're going to look at now. And does everyone know where this image comes from? Many of you, I hope. No. Well, wow. The energy in this room is palpable. We really are at a science conference. Okay, so I'm a musician and a sound artist, so I work with sound. So the obvious thing to do is to look at, is there a way of turning genomes? It's the Center for Genomics and Systems Biology. Is there a way of turning genomes into sound? What would that be? What would that look like? What would be interesting to us? And how can we convert that data into something that could potentially be meaningful and something that looks at rethinking about our understanding and experience of biological data. And so for that, we looked at this idea of turning transposable elements into sound, focusing on the abundance, distribution, and variation. And we started with the human genome. And so what we did is we started with chromosome 21 and looked at taking the wonderful data from the UCSC genome browser. That's that image there for those who need to brush up on our visualization of the genomes here in this room. And this is actually, in fact, that you're looking at right now is the section, I'm going to play a section of it, and that's the actual section we're going to hear that we worked on. So I promise I won't go into all of the very details, as I may have gone last year, because I want to give you an update. But essentially, we're turning both data and a static visualization into a temporal experience, so we have to do a couple of things. One, we have to assign pitch to something. And so here, we started in the very first realm, we started at looking at mapping the rep classes, the large rep classes, into individual pitches, which means just every time we hear a particular note, that will focus on that particular transposable element. Very simple. The other thing is we had to make a temporal relationship. So we had to take a tempo. We had to create a tempo, and in this case, it's 2,000 base pairs. When you see and hear what we're going to listen to, you're hearing, and there's a new visualization, you'll see 2,000 base pairs passing by every second. And now, of course, what that gives us is note duration or length. So if there is a LTR that's 4,000 base pairs long, for example, you're going to hear a G natural, and it'll be held for 2 seconds. So far, so we have pitch, we have duration. Then we also have, of course, as we know, this fabulous double helix, so we had to also separate those things out, whether we hear it on a plus strand, or whether we hear it on a minus strand, we had to kind of think of ways of doing that. And so what we did is, that's to do with instrumentation and octave, which just means anything you hear on the plus strand is played by a gong, anything you hear on the minus strand is played by a bell, anything that's on the plus strand is in octave 3 and doubled in octave 4. Anything that's on the minus strand is just in octave 4. So now, if that same LTR, that's 4,000 base pairs long, appears on the plus strand, it means you're going to hear a G natural held for 4 seconds. It'll be played by a gong, and it'll be held, in octave 3 and 4. Great. So I don't need to explain this stuff to you because you already know what's happening here. But with the transposable elements, in terms of when they have entered our genome, because we have that information, we looked at ways of how we could represent that. And so because we're programming things in MIDI, we have this thing called velocity that is scaled. And so just like in our, the scaling of when things entered our genome, we have from 0 in this section, 0 to 403 million years. We use MIDI velocity, and MIDI velocity is 0 to 127, which just means how hard or loud something is. If something's very soft or it's not struck very hard, it's at 0 in MIDI. And if it's something that's really hard, struck very hard, in this case, our gong and our bell, it's at 127. So we just reverse those things. Anything that's old in our genome is at 0 or close to 0, and it's scaled up to anything that's loud is at to 403 is up to the scale of 127. So that what you hear now is when you hear a note, its relationship to all the other notes is now present in age, essentially representing the transposable elements. There's also accompaniment. And the accompaniment makes sense. No, we can... we can go into it, but essentially, you'll hear chords in the background. If you're like, well, why are there chords in the background? Well, the chords are, of course, made up of the percentages of A, Cs, Gs, and Ts as they pass by. As they pass by, as we're reading them, it's not just the transposable elements, but now we're making chords to understand what percentages of A, Cs, Gs, and Ts are happening at 8,000 base pairs in the background of all those things. Okay, so there's some sound. The other thing is, as you saw, as you all know so very well, this visualization is very boring. And it's not interesting in any way, shape, or form. So I thought, well, we had to redo that and look at something that we can follow along with. In fact, I believe if you saw out on that big screen today, and it'll be floating around, it's what you're seeing. What you're seeing on that screen was produced here at the CGSB. It's a visualization of the same section of the human genome looking at transposable elements. And what you're seeing out there on the screen, and what you're going to see here now, is that each transposable element category is being represented by a fixed colored light. That's them there. So if you see them outside, or you see it in here, this is what's happening on the screen. You don't need to know any of this. You can also just listen to it and be like, oh, that's kind of pretty or nice. And that's the goal of it in some ways as well. Yes, we can understand patterns in what's happening, but in terms of the design in the background, it's also supposed to be something that has meaning. It has meaning to those who want to delve into it, but the goal is that it's not, no one has to. No one has to know here. We are just, after all, listening and looking at abundance and variation in these transposable elements. And if you want to walk past the installation, you are so welcome to do that. So here, the idea is that the lights, they turn on. So again, our fabulous G natural turns on, and if it turns on for 2 seconds, it's 4,000 base pairs long, for example. And as it turns on, it sends a stream of particles out, and those particles start to spin, and they spin one way for the plus strand, and they spin the other way for the negative strand, so that you can start to see the double helix. That's the idea. Great. And then that wasn't enough. So the idea is also we're having those chords in the background. And so I wanted to, because we've created a three-dimensional digital space here, we can also use the principles of light installation to then visually show those percentages of ACs, Gs, and Ts. So if you were to pay special attention to the background behind those TEs, you'll see percentages of ACs, Gs, and Ts in the idea of percentages of light, so that we can flood the background with a hue that's based on things like if there are 23.3% A in this, as it's reading our system, there will be 23.3% blue in the hue of the light. Okay. That's enough out of me for a moment. We have a little look at how it turned out. And I'll play you a sample, and then I'm going to give you an update on what we did for a public installation here later that happened in November. So here is what you're seeing out there. This is the very first iteration of what we're working on. And perhaps we can turn it up at the back there. So the visuals outside, it doesn't have sound. This is what you would be hearing if we did have the sound on that screen outside. I have limited time. There you go. Okay, so it turns out my timekeeper told me I have limited time. I didn't think I was speaking that much. Okay, so that was the first iteration of it, and what we did is we updated the pitch map of these things. So we're adding more complexity. The idea is looking at ways we can incorporate more data and in more ways. So what we did is then perhaps some of you know, there was an event here in Abu Dhabi called Expanse. It was this idea of looking at the future with exponential technologies. And I was fortunate enough to be invited to create 2 installations. One of them was indeed the NYUAD, the CGSB project here with Transposon. We incorporated, this is an LED screen now, and so in the visuals now we also have things like the actual base pair data that's being read underneath in the program, happening at the same time, and with the updated pitch map. So it sounds different, it's updated, it's much more complex. They're the real heroes, the people setting up the screen, by the way. See there? There, yeah, that's the hard work. Oh, last comment, the photo I really like is the one at the top left. And so I have a comment, if you really want to change people's mind, make something they can touch. So if you want to really change policy or change science or change art, if you make a museum where people can touch things, people love touching. This is an LED screen, it's not doing anything. But every time I would turn around, someone would be there. It's like this, that's just like going like this. So that was what I learned coming here, is make things that people can touch and it'll change their mind. So there's a big update on those things and it's much more complex. We don't have time to listen to that because I wish to show you one more, the project that started with John Bird. But the collaborators here, of course, Stéphane Boisineau and particularly Giuseppe Antonio Saldi. So we said there's a program reading that information. That's all his fabulous work there in the background. Okay, so in my limited time, I'll give you a quick rundown of this and show you a short video that was produced here by the CGSB for this project, and then you can ask me some difficult questions. So the other thing we did was the idea of starting the very first soundscape study of coral reefs in the Arabian Gulf. So right now, there are hydrophones, there are underwater microphones out in the Arabian Gulf, and they're recording the sounds of those coral reefs. They're recording how noisy they are, what's on those reefs, and kind of how that changes, whether it's in the day, night. Ideally, seasons and across years would be the goal of doing this project. So the idea was it was to produce both scientific and artistic outcomes. And so on the artistic side, for those of you who know either remember or know the Voyager, the golden records that were sent on Voyager, of course, had sounds of the natural world as well as sounds of the human world sent into space, connected to hopefully, sending it out for our alien overlords to come and help us out here on Earth. And so I had the idea of taking Sagan's comment, which was the idea of casting a bottle into the cosmic ocean. Isn't that beautiful? A bottle launched into the cosmic ocean. And so I thought, well, we're recording the sounds of these coral reefs, and in addition to the climate crisis, which is affecting so many things about them, the idea was, to make, instead of a golden record, is to make a plastic record out of the material that's in the very real ocean and send it back to us as a reminder of our contribution to the ecosystem that's down there. And so there's my dear friend Araib El-Katan, both at the back there and also on screen, holding our very first 3D printed attempt at making plastic records. And we were looking at ways we could do this in-house, what we had here at NYUAD, what was in the ERB, and the knowledge that we had to both do it for 3D printing and then also cut into the actual material we were collecting from the Gulf. So that was a really quick overview, but I have, the last thing I'll play you is one video that we made at the beginning of this project. It's still in process, and we're still looking at what we will do with it and where it will go from here. But here it is. Oh, you'll see, I will just warn you, I'm also speaking in the video. This guy won't stop. I'm also speaking in the video, but you also notice, I don't want any, I'm warning you, because I did this recently at NYU, big NYU. There's NYUAD, and then there's NYU in New York, and there was some shocked faces because, I didn't have a beard then. So I'm just warning you now, this is when I was young and handsome, and now it's like, look, the difference a year makes. So here, this is the project we've been working on. This is the sound of a world in distress. My name is Sam Nestor, and I'm the artist in residence for the Center for Genomics and Systems Biology at New York University. With marine biologist Dr. John Bird, we've begun the first aquatic soundscape study in the Arabian Gulf, listening to the underwater world during a time of climate crisis.
I'm interested in the Arabian Gulf because it is the world's hottest sea. And if we're interested in things like climate change, this really serves as a model ecosystem, a natural laboratory for us to try and understand how marine fauna cope with and respond to extreme temperatures and what that means for things like coral reefs and reef fishes in other parts of the world in the future.
These fully submersible, long-term deployable hydrophones have been fixed to data stations throughout the Gulf and are recording the otherwise hidden acoustic environment. These passive monitoring devices are tracking the diurnal rhythms that occur in and around reefs throughout the day, night, across seasons, and ideally years. This interdisciplinary project aims to produce both scientific and artistic outcomes.
One of the things that coral reefs do is they produce a lot of noise. And this noise is important because it's an indicator of biological activity. So you've got shrimp and fish and crabs and sea urchins in there operating at different times of day and night, all of them producing these sounds. And there are some suggestions that as reefs become less and less healthy, we get a change in that acoustic signature of reefs, such that we start to hear differences in how these reefs sound as they go from being very healthy environments to ones that are relatively degraded.
Hear a diversity of human sound affecting life among the water, from commercial shipping, recreational fishing, jet ski motors, and divers. The sound of the marine world is changing, and not for the better.
We have a number of recurrent bleaching events here that are related to marine heat waves, and these heat waves are becoming both more frequent and more severe. Changes in the acoustic signatures of this reef, it may have broader implications for biodiversity on these reefs itself going forward.
Recordings we are capturing, I developed a project with scientists and engineers at the university to create discs made out of high-density polyethylene ocean plastic to play the soundscapes of these reefs on turntables. Shot. Outside of the scientific study that is being conducted, the goal for this artistic project is to capture the natural environment as it exists now and make commentary on our contribution to it, the sound of the ocean through the plastic that is choking it. The degraded audio that comes from reconstituting this plastic is itself part of that commentary. We really are hearing the sounds of these material dumped into their environment.
The work with SAM has been incredible for us because it gives us a chance to think beyond science and into areas where it will have more impact with society as a whole, because this is something that people can and support and really understand. If you can hear this change in acoustic signature that's resulting from marine heat waves, it really does give us very visceral feel for what's happening to these coral reefs and the impacts that we as a species are having on the entire world.
The hope for this project is that it amplifies the very real stress that is being placed on a part of our world we still know little about, but our actions through the climate crisis and pollution are continuously damaging.